So last time we saw that if F is adjoint to G and F is exact, and these are functors between two triangulated categories, C and D, I guess. C and D, triangulated categories. Then G was exact. And this was an if and only if. If G is exact, then F is exact. So today, I want to construct a triangulated category out of an abelian category. So let's suppose that A now is an abelian category. Remember, we have this category of chain complexes or co-chain complexes on A. I'm just going to talk about co-chain complexes, but the same. So this is the category of complexes, so co-chain complexes. And this is an abelian category as well. This is also an abelian category. And then in general, it's not triangulated, but the failure of being triangulated was minimal in the sense that we had a candidate. If we have a map of complexes F, then we can always extend this to the cone of that F, and that this guy came with a map to A shifted by 1. But this could not be declared to be a distinguished triangle because we had the problem that this guy is quasi-isomorphic to 0, but it's not 0. And we needed to have isomorphisms between this guy and 0. So this one is not, this category is almost never triangulated. But we constructed another category. Remember, we had this category which was the homotopy category of A. And this category had as objects the same objects as chain complexes of A, but morphisms were different. But morphisms in this category, well, morphisms here, were equivalence classes of morphisms in here, namely, given two objects, given two complexes A and B, then homs in this category, in the homotopy category, yeah, probably hom is a bad idea to use as for a name. Let's call it K. Hom for homotopy is not good. Let's call this guy K, the homotopy category. Then hom in this category K are homotopy classes of maps in the category of cochain complexes of A between A and B modulo homotopy equivalence. Okay, so that made things slightly nicer. This, first of all, the first observation is that this is an additive category. We checked this, that we could add maps modulo homotopy. So we have a functor from cochain complexes on an abelian category to this homotopy category. It's a well-defined functor. If you have A, it maps to the same object. And if you have some F that is a map between A and B, then it maps to the class, the homotopy class of F in Hom K of A between A and B. And this is a functor. This is a well-defined functor. This is something we've already checked. But that homotopy category is actually a triangulated category. And this is something I've never checked. But K of A is triangulated. Let's get there later. I want to construct another category, which is perhaps more important, which is the derived category of A. So let me state this as a theorem, which is an existent theorem. There exists a category D of A and a functor from coaching complexes of A, an additive functor from coaching complexes of A to D of A, such that any quasi-isomorphism on A becomes an isomorphism on D of A. Such, let me call this functor F, such that if F is a quasi-isomorphism between A and B, so not, well, this I should probably say quasi-isomorphism. Remember, this is a map of complexes on A, from this complex to this complex, that induces the identity isomorphism, that induces an isomorphism in homology. So quasi-isomorphism means the F is an isomorphism between the homology of this complex and the homology of the other complex. Then this functor applied to F is an isomorphism. In G of A. So that's one condition. I mean, of course, this condition is kind of silly because you can take this category to be the empty category. If you want it to be an additive category, it's just the category, the zero object and the zero morphisms and nothing more, and then this is true. But then the second condition is more important, is that for any other category, D prime, and a functor F prime between the cochain complexes of A and D prime with the same property, then it factors through D of A. Well, we have these cochain complexes of A, our functor F to D of A, we have our functor F prime to this D prime, and then this guy exists, making this diagram commutative. Okay, so that makes this D of A non-trivial. All right, so let's prove that this exists, and let's prove that this exists by constructing this D of A. And this D of A is going to end up being a triangulated category. So this is called the derived category of A. So D of A is called the derived category of A. This A. All right, so the first observation is that quasi-isomorphisms between A and B, well, they need to be invertible. They are isomorphisms in D of A. The second observation is that any object on this category of complexes should give me an object in this D of A, and this, by this universal property, then I need to identify, at least this guy should have as many objects as this. So, so the first observation is that I'm going to declare the objects of D of A to be the same as the objects in the homotopy category. And these themselves were the same as the objects in this cochain complex. So these are just complexes. So the objects are the same, are just complexes. The problem is in the morphisms. And let's suppose that you have two complexes. So let's say that I have some A and I have some B, two complexes. The question is, what is a morphism in this category D of A, between A and B? But now let's suppose that I have a quasi-isomorphism from a C. Oops. From a C into A. Suppose that you have some quasi-isomorphism. So this guy here is a quasi-isomorphism. Then any morphism from C to B, a morphism, homomorphism in the category of cochain complexes, should induce a morphism from A to B in the category GA. Is it clear? So, first of all, any morphism from C to B should be a morphism in the derived category because I have a functor, F. So for any morphism between C and B, I should get a morphism between C and B in the derived category D of A. That's just the fact that I can apply my functor to this morphism here. On the other hand, the fact that C has a morphism to A gives me a map from C to A in the derived category, again, because it's a functor. But now this map is invertible in the derived category, because I've just declared that maps, the corresponding map to a quasi-isomorphism is an isomorphism. So that means that in the derived category, I have an invertible map here and a map here, so I can compose the inverse of this with this functor, with this morphism, to get a morphism from A to B. So even though in the cochain complexes, I may not have a map from A to B, whenever I have this situation, I should get a map from A to B. So let's define those to be the morphisms. So definition, which is not a good definition still, the set of morphisms. Hom on the derived category A to B is going to consist of guys like this. I'm going to start dropping this dot, and every object is always a complex, where this is a quasi-isomorphism. Now this is not good enough. This is not good yet. And for two reasons. First of all, I need to identify a few of them. So this is just too large. If I just replace C by a quasi-isomorphic object, I might get the same morphism from A to B. And it's going to be a different diagram like that. So for example, I could just take a different C. So this is not good enough, and I need to mod out by equivalences. Let me tell you what those equivalences would look like. So the question here is like this. So suppose that I have a morphism between A and B. Let's forget about this. These are all complexes. And now this is a quasi-isomorphism. So whenever I write this dot is not an isomorphism, it means a quasi-isomorphism. And let's suppose I have another guy. And this guy is also a quasi-isomorphism. But actually, no. Let's do this the other way around. So let's suppose that you have another guy, which is quasi-isomorphic to this C. Then you can now compose this map. It gives you a map here. This is just the composition of this map that you had. It's just here. And then this composition is a quasi-isomorphism with a quasi-isomorphism. This should be the same map from A to B. Because as a map from A to B in the derived category, this is just the composition of the inverse of the corresponding map between these two with this. But then that's the same thing as just going back, going to the inverse, and then applying this map. Because that would be the same as going like this, then the inverse, then this map, and then this map. So it's clear that this diagram, C prime A B, should be the same as the diagram C A B. So it's clear that these two morphisms as morphisms from A to B should be the same. Okay, so if you play a little bit more, you're going to realize that the following is the actual equivalence class. So let me tell you what the equivalence class is. And that's going to be a good definition. Okay, so I will declare that if I have a morphism between A and B that looks like this, again, this is a quasi-isomorphism. I'm going to just put it a Q. And I have another morphism between A and B, so that's given by this quasi-isomorphism, and a map to B. I will declare that these two maps are equivalent. If there exists some C prime fitting like this, some C second prime fitting here like this. So it's a diagram like this, where this is a quasi-isomorphism. So this is very similar to what I did there. So this C second prime gives you a map from C to C prime in the derived category. But the condition, and this is a strong condition, well, not strong, it's a weaker condition, such that this diagram commutes on the homotopy category phi, and not necessarily on coaching complex. Okay, so what am I requiring to identify this morphism from A to B with this other morphism from A to B? I'm requiring that there exists a complex with maps to C prime in such a way that, in particular, for example, this composition here and this map from this complex to C prime and then to A, these are two different maps from C second prime to A. And those two maps do not need to be the same map, but they need to be homotopy equivalent. So if I would require that this diagram commutes here, those two maps would be the same map between the two same complexes. But I'm requiring that this diagram commutes on K of A, and commuting on K of A means that this composition is equal to this composition on K of A, which means they are equivalent, which means they are homotopy equivalents. Okay? So everything here, all of this diagram is homotopy equivalent. This composition here is homotopy equivalent to this. And what else do I have that it's commuting here? So this composition here is homotopy equivalent to this. Now, so that's going to be my equivalence relation. And this is the definition of the space of homs. So we need to check that this is an equivalence relation. So that's a well-defined space of homomorphism. So the theorem is that GA with these morphisms is a category. So we need to check several things. We need to check, first of all, that the space is well defined, that the space of morphisms is well defined, namely that that equivalence relation is actually an equivalence relation. And then we need to prove that we can compose morphisms. So I think the hardest thing is to prove that we can compose morphisms, but let's make some trivial statements about the good definition of that. So I need to check, for example, that that a morphism is equivalent to itself. So if I have C from A to B, quasi-isomorphism here, and I have the same quasi-isomorphism here, so this is the same diagram, then I can just take the identity, which is clearly a quasi-isomorphism, C, and the identity here, and everything here actually commutes on complexes. So this means that this morphism is equivalent to itself. So this relation is, what is it called? Reflexive, when something is equivalent to itself? I never remember these things. Whatever, it's equivalent to itself. So let's suppose that you have something that is equivalent to, we have this situation and we have some C prime, and that these two guys are equivalent. So this guy exists. I'm making this diagram commute. Then the map from A to B, this map is equivalent to this map. So for that, I need to check that the same C second prime is going to be given, but I need to check that this is a quasi-isomorphism, that this here is a quasi-isomorphism. But that's clear because what I had is that this guy is a quasi-isomorphism, and this map here is homotopy equivalent to that. And we've checked before that if you have two morphisms between complexes, so if you have two complexes A, well, I guess different ones. So in this case, I have C and A, two complexes, and I have two maps between the same complexes, F and G. F and G are homomorphisms of complexes where F is a quasi-isomorphism and G is homotopy equivalent to F, then G is a quasi-isomorphism. This is clear because by G being homotopy equivalent to F, it induces the same mapping homology as F does. And F is an isomorphism. So that means that G is an isomorphism in homology. And since G is a map of complexes, then it is a quasi-isomorphism. OK, so that means that if this morphism in the derived category is equivalent to this guy, then this guy is equivalent to this guy. So this relation is, I don't know, I guess I would call that reflexive. I don't remember the names for these things. Symmetric, thank you. It's symmetric. The last one should be easy because it's transitive then. So we need to check that this relation is transitive. So let's suppose that you have some, so now I need to have three maps that are equivalent between themselves. So I have that this morphism is a morphism from A to B, and I have another morphism from A to B, and these two guys are equivalent, so there exists this guy making this diagram commute up to homotopy, and I have a third one. So again, this goes to A, this goes to B, and this is equivalent to this, so I have a fourth guy here making this diagram commute. Then what I need to do is I need to construct something that makes an equivalence between this map here and this map here. So I need something that maps to C and this C and this guy here. Can anyone construct this? Okay, so if I have an equivalence between this map, this morphism from A, I can think of this C as a map from A to B. The C prime is the roof of a map from A to B, and then this C 3 primes is a map from A to B. These two are equivalent, so this exists, and this is a map from A to B. These two are equivalent, so this exists, and this is a map from A to B. What I'm looking is an equivalence between the first and the third one, so I need something on top of this C 3 prime and this C. So I need some complex with maps to C and to C 3 primes, making everything commute. Okay. Como que a gente constrói esse pullback? I'm sorry. Yeah. Yeah. So Tadeo is suggesting we pull back. So something here we want. Okay. And how do we construct that something there? But that's the right thing, kind of thinking, and we're going to get there when we actually compose morphisms. So let's at least analyze this case first. So we're looking for a complex and maps. What we actually need is a map from C to C and to C 3 primes. Clearly something that maps to C second prime and C 4 primes is going to give us such thing by composition. So okay, that's a good idea. But how do we construct that map? That complex. So the category of complexes has fiber products. So we can actually take the Cartesian product, for example, here. We can just take the direct sum and the equalizer to this map, or these two maps to C prime. So that's the sum of these two things modulo those things that map to the same guy here. And that's going to be some complex with maps here and here. But that's going to fail blatantly. So that's a natural thing to put here, something that is the Cartesian product here. But that's bad, and let's see why that's bad. But again, so in order to have well-defined these morphisms, what we're missing is sort of like filling in this diagram. Let's suppose that we have such a thing. Let's suppose that we have, let's start putting C5. Let's put a different object, D there. And let's suppose that we can make this thing in such a way that this is a quasi isomorphism. If that happens, then this composition here is a quasi-isomorphism, and if we make it in such a way that this diagram commutes up to homotopy, then all of these compositions here are going to be quasi-isomorphism. So anything that starts from D and ends in A is going to be a quasi-isomorphism because it's going to be homotopy equivalent to this map, which is a quasi-isomorphism. And that's going to give us, therefore, an equivalence to this guy here, because I can just take this map, D to A, and then D to C 3 primes to A, and that's the thing that we are looking on top of C and C 3 primes. So the trick here is what we want is we want to construct this D prime in such a way that this guy is a quasi-isomorphism and that this diagram commutes up to homotopy. So this is what we need. We haven't solved that problem yet, but let's try to deal with composition of morphisms, and we're going to solve that problem in a larger setting. So what I claim is this. Suppose that you have a morphism of complexes A, B. This is a map of complexes. And you have some C, an arbitrary map here. So let's put names. This is F, this is G. Proposition. Suppose that F is a quasi isomorphism. F is a quasi isomorphism. There exists a unique filling D and maps F prime, G prime, F prime, G prime, making this diagram commute. This diagram commute. But this diagram commutes not on cochain complexes, but up to homotopy. And F prime is a quasi isomorphism. And I think this is the key point here. If I have complexes A, B, and C, I can always pick D to be the sum of these two things, and then the subcomplex of that sum where I equalize the maps F and G. That gives me something that maps to A, maps to C, and that makes this diagram commute on the nodes in the category of complexes. But the problem is that this thing is just too large and it's not a quasi-isomorphic map to this. So now if I want to keep the fact that liftings of quasi-isomorphisms need to be pullbacks, need to be quasi-isomorphisms, then I lose commutativity at the category, in the category of complexes. So this is the thing that we need to relax. So I can find something such that this is still a quasi-isomorphism, but then now this composition here is not the same as this composition here. They're just equivalent maps up to homotopy. So let's prove this statement. And this is non-trivial. And to prove this theorem, we need to remember, we're going to use this cone that we constructed several times, and we used a lot of times. So the first observation is this. Remember that whenever we have a map, let's recall some conditions about the cone of a map. If I have a map of complexes, I can always complete this. The cone was a complex with a map from B to that cone, and I had a map from the cone to my first complex shifted by 1. Moreover, we were careful when we constructed that cone in such a way that this composition here is a short exact sequence of complexes. B to CF to A shifted by 1. This is a short exact sequence of complexes. Remember what this guy is. So if I look at the term in degree n, I have here Bn. If I look at this term in degree n here, this is Bn plus A shifted by 1 in degree n, which is An plus 1. And this guy in degree n is An plus 1. So that's... And this sequence is really just the inclusion of Bn in the first summand here, and here is the projection into the second summand, and this is clearly an exact sequence. In particular, the composition of this map to here is the map 0 of complexes. On the other hand, I could have looked at this sequence, which again, in a triangulated category, we've checked that the composition of two maps, any two maps, in a distinguished triangle is 0. But that composition is not 0 for the cone. So for the cone, if I look at this guy in degree n, and I look at B in degree n, here I have the map F, and then I look at the cone in degree n, what I have is Bn plus An plus 1. Now, F, the kernel of this map is non-trivial. It doesn't need to be trivial. So I will have the kernel of F mapping there. And the co-kernel of this map is just the inclusion. It's just the map from B to Bn is just the inclusion in the first factor. I don't know, I'll call it iota. So this is injective. So the kernel of this map is 0, which is not the image of this map. So this is certainly not exact anywhere. Okay? However, so this is not exact. However, the composition of this map here is also not 0. It sends A to f of A, and here it goes to f of A, 0. So this composition is non-zero. But it is homotopy equivalent to 0. And this we've also checked. Okay, so that's one observation. All right. So let's look at what do we have when we have a cone. So let's suppose that we have a map F between between A, B, F, and here I have the cone of F, and here I have A shifted by 1. So let's do this in a different board. So again, I have A, B. This is my map F, and here I have the cone of F, and here I have A shifted by 1. Correct. So now, remember that we have a map also. Remember we have a map like this. From B to the cone of F to A shifted by 1. So everything here is the same as what we have there. But now this maps to B shifted by 1. And here is just F shifted by 1, which essentially is just minus F. On the other hand, this is a map of complexes. And if this is a map of complexes, let me put H to be that name, that map. Then I have the cone of F, of H. And then this maps to be shifted by 1. And I have here the identity. I have here the identity. I have here the identity. And if I was working on a triangulated category, and these were distinguished triangles, then I would get an isomorphism here. Okay, I get an isomorphism in such a way that this is an isomorphism of distinguished triangles. But this is not a triangle. These are not triangulated categories. However, the statement is that if I have this, then there exists a map here. I have F, G. The statement is there exists G, which is an isomorphism in the homotopy category. So this is certainly not going to be an isomorphism of complexes, but it's going to be something that is an isomorphism in K of A, making this diagram commute in K of A. And notice that we need to pass to K of A because we have this problem that the composition of these two maps in the cone, the composition of the map from A to B to the cone of that map is not 0, but it's something that is homotopy equivalent to the map 0. Okay, so how do I construct this map? Okay, so I want to prove that this map should be a map of complexes. So morphisms in K of A are not fancy things like the derived category that there are these roofs. A morphism in the derived category from A to B does not need to come from a map from A to B. But this guy actually needs to come from a map from A to this cone because I'm saying that this is in K of A. And morphisms here are morphisms in coaching complexes modulo something. So this G is the equivalence class of a map of complexes. Okay, so this guy here in degree n is Bn. This guy here in degree n is Bn plus A n plus 1. And this guy here in degree n is therefore the cone of f in degree n plus b in degree n plus 1. And the cone of f in degree n is this. So this is bn plus a n plus 1 plus bn plus 1. So what I'm looking is for a map from this guy in degree n, which is a n plus 1, to this guy, which is a map of complexes. But for that, I need to remember what were the differentials on these two guys. And I'm going to get the signs wrong, so I reserve the right of getting one sign wrong, and therefore all signs wrong. But what is the differential here? Okay, so I need a map. Now these are co-chain complexes. These are not chain complexes. So the differential increases degree. So the differential in the C of f is a map from that to Bn plus 1, An plus 2. Okay. And I can take the differential on Bn here. I can take the differential on An here. And I get a map from An plus 1 to Bn plus 1 f. And I don't remember the book. I think the book actually chooses to have minus f here and minus d here, or probably minus d here, and then plus in these two. I don't care. Okay. So there's some choice of signs to make this into a good complex. But the point is that something from here just you apply d, and something from here you take d on this component and f on the other component. That is the differential on C of f. Therefore, the differential here, well, it is on this C here, is this differential. So therefore, the differential here looks like, well, probably I need to start moving to a different, I'll keep this because we need this, we haven't solved that little diagram there. But what we're looking for is a map from this to Bn plus 1 plus An plus 2 plus Bn plus 2. And the map from Bn here, this piece here is this. So it should be the same as this. So from Bn, I just go to Bn plus 1, applying the differential. So this thing here is just d. From An plus 1, I go to applying f with some sign here and d here in the complex A. And this Bn plus 1, what does it do? This is the most complicated one because it takes d into Bn plus 2, but it also takes the differential, this takes the map h in this other component. And the map h is the identity map here. Okay? So the map from here into this complex is d on this component plus the inclusion in this guy. Okay. So let's check if we actually have a map So what we're looking is for this map G that should go from A shifted by 1 to this C of H. So what we want is this into Bn plus An plus 1 plus Bn plus 1. And the naive thing to think is that you're just going to take the identity here. Okay? So this is our G. That's just going to take some A here, and it's going to map it to A here. If I do that, the differential here goes to An plus 2, and it's going to just give me dA. And if I map here to Bn plus 1 plus An plus 2 plus Bn plus 2, if I compose this way, I'm going to land here in dA, in this guy. On the other hand, I checked that the differential here on the A side wasn't dA. It is dA into here, and then plus F here. So if I compose this way, I don't get to dA. I would go to A, and then here I'm going to go to dA plus F of A here. So we fix that by not using the identity here, but also using here the fact that we have the map F. So and I'm sure I'm going to get the signs wrong. And since I never computed the signs there, I claim that doing this, so this is A in this side and minus F of A in this component, fixes everything. So if I map this way, I just go to dA. And if I map this way, I would go to dA here minus dF of A. I'm sorry, or F of dA. It doesn't matter because F is a map of complexes here. And if I compose this other way around, well, this A here goes to dA plus some F of dA. And then this F of A here will have a bunch of components. The guy here goes to d of F of the A. So that's going to kill or add one more of this form. And there's two more there's one that gets killed by itself because of the d of this guy itself. Well, let's compute this. Let's compute what the differential of this component to that component is. Okay? Which is this minus FA is going to go to minus, except with a sign, but it doesn't matter. So this is going to go to minus d of FA, which is equal to that because of the fact that F is a map of complexes. So this is d applied to the second component. Plus, I need to look at the map from Bn plus 1 into the cone of F. So I need, remember that the differential on the cone is, on this guy is d plus the inclusion of this Bn plus 1 into the cone of degree n plus 1. And this is just the map H. This is the cone of H. And the map H, well, I need to describe what the map H is. So I'm looking at H of this d of minus F of A. Okay, what is this H? Well, this is the map from Bn, in that case is Bn plus 1, to Bn plus 1 plus An plus 1, which is just the inclusion of Bn. So this thing here maps to this thing here by just the inclusion, which is minus Fa. And now, this composition here and this composition here are not the same, but they are homotopy equivalent. So what I did is I killed this F of dA, which was the nasty one, and I've got dA minus Fa on these other two components. And that's the same thing going the other way around. Okay, so this guy here makes this diagram commute. Oh, we need to check that this makes this diagram commute. We just constructed this guy being a map of complexes. Now we need to check that all these diagrams commute. this is probably just too nasty. Let's check a couple of them. So here, this is obvious that they commute. There's nothing to check. So this, by definition, was H. But I need to check that this and this diagram commute. I don't want to do this. Let's probably check this. Let's just see how nasty it is. So from the cone of F to A, and then apply G, and then to F, and then apply this cone of H. Yeah, I don't think we're going to have time to check every little detail that this diagram commutes, so I'll leave this as an exercise. Exercise, check that this commutes. Check that both diagrams star and star star commute. Because I want to check something more complicated. So these two guys commute. Oh, star and star star. What we need to check, though, is that this is an isomorphism in K of A. And that's easy. Because the inverse, I need to give you this inverse here. And actually, yeah, I can probably check quickly that this star commutes. So I need to tell you what is the inverse map from this guy into A shifted by 1. And that is a map from Bn plus An plus 1 plus Bn plus 1 into An plus 1. And this is just the projection on the second guy, on the second component. So the map from that to there, that's just simply the projection into the middle factor. And then that's clear that the composition in this direction is just A. It just kills this f of A. So the composition in this direction is isomorphic to the identity. Now the other way around, you need to check that if you apply the projection and then so if you do this and then you come back here, you don't come back to the identity, you come back to A minus f of A. But then again, we've already checked when we checked that the cone was quasi-isomorphic to 0, that map that sends A to A minus f of A is just homotopic equivalent to just sending back to A. So it's clear that this G is inverse to this pi. And actually, you can use that to check. So you can use that this projection into the middle factor is the inverse of this G to check that this diagram commutes. OK. But now let's prove this, which is what we ended up setting out to prove. So now that the cone satisfies that nice property, so now I know that I can replace, so if I have any map of complexes, then I know I can fit the cone into a sequence like this. And now I know that I can replace my A in the homotopy category by the cone of the cone. Okay, so here's now is the situation. I have this A to B. I have this C. And I would want to construct something that maps to both, that map to A, and that makes this diagram commute. So let's see, what do I want to do? How do I do this? So now I want to prove that lemma there. That if F is a quasi-isomorphism, I can lift it by being a quasi-isomorphism. And this shouldn't be hard, so let's check this. Oh, I'll need an extra lemma. Well, let's prove that in a second. Okay, so let's see what we can do. So we can A, B, the cone of F into A shifted by 1. Now that diagram there said that I had from B to the cone to A shifted by 1 to B shifted by 1. So let's look at that. B to the cone of F to A shifted by 1 to B shifted by 1. And what I had out of that diagram, so perhaps I should need a different board, but what I have is from B to C of F to the cone. So if this is H to the cone of H to be shifted by 1. And this was invertible. So I had an inverse here in the homotopy category. This is the identity. This is the identity. What I'm looking for is to shift this G. So let's see. Right. Okay, so what we're going to do is we're going to replace this A by that cone, by the cone of H. Because we know that these are isomorphic in the homotopy category. And what else? Oh, I'm mixing things. So just a second. If I shift this A by that cone. Replace my A with the cone of H. Okay, let's see what I want, and let's see if I can construct. The first observation, so this is what I need to construct this G. And I want to check that I have a quasi-isomorphism. Now, why am I using the cone everywhere? It's that I know that the cone of a quasi-isomorphism is quasi-isomorphic to 0, which is something we've checked several times. So I know that this guy is the same thing as 0 in the derived category. So one checks that things are quasi-isomorphisms. So let's suppose that I told you the other way around, that this is quasi-isomorphic to 0. By looking at the long exact sequence in homology, you check that this F induces isomorphisms in homologies. Because these guys are 0 in homology. So that means that this F is a quasi-isomorphism. So the same thing we want to do this here. What we would want to have is a map between these two such that whatever comes next is just a cone that we happen to know that is quasi-isomorphic to 0. So that has to be the only thing that is the datum that we have, that is the cone of this F that we know is a quasi-isomorphism. So what we want is a map from C to the cone of F. right? Because that we know is 0 in homology. And then whatever we construct this D into that, so if we construct something like this, then we do know that this has to be a quasi-isomorphism. Right? Because this guy is the cone of a quasi-isomorphism, it has to be 0. So how do we do that? And that's a good question. Okay, so what I have is a map like this, a map like this. But this is what we have, where this is my F now. So I'm looking to construct this side of this diagram, and here I have this G, and here I have this identity. And I'm trying to construct this thing, but I don't even know what this D is. So I'm trying to work backwards what is the thing that we want to construct. Okay, so I think this is what I've called H. Now, what I do know is that this thing here was isomorphic in the homotopy category to this cone of H, to this H that I have here. So I have from B to C of F this H, and I had this cone of H here, and I had this A shift, this B shifted by 1 here. Okay, but then what I can do is just shift this triangle to this, to the cone of H shifted by -1. And this are isomorphic in the homotopy category. So this is the identity, this is the identity. Okay, so now I claim that, therefore, this guy here fits as my D. So let's check that that's true. Let's check if that's true. And why would that be true? Anyone seeing how to? What am I messing up? So I think that the cone of H there should map to D, making this a whole diagram commute. Well, it should be that D. So let's check if that's true. What am I doing this wrong? Oh, I see. Okay. Yeah, we can do this. This is just the construction of the cone of F here. This is the datum G that we're given. And we have a map from C to C of F to the cone of F by just composing these two guys. So let's put that here. So that's a map like this. Now, this is a map of complexes. And as a map of complexes, you can continue it to the cone of that map. And this goes to C shifted by 1. But let's not forget about this part. Let's forget about this. But you can always continue it like that. Now, so here's the point. here I have the cone of H composed with G. And here I have the cone of H. I claim that there's a natural map from here to here. So let's write this as a lemma. So as not to overload too much, if I have, so H and G are the complexes. So if I have complexes and maps like this, I think I'm composing H after G. The A and B and C are not going to be in the same, but at least I want to compose them in the same order, G first and then H. Then I have the cone of H composed with G, and I have the cone of G, of H. So here in degree n, what I have is Cn plus An plus 1. And here in degree n, what I have is Cn plus Bn plus 1. And what I would want is a map that commutes with the differentials. So again, if I have a C here, it maps to D of C. And I want to map it here. And if I have a C here, it maps by the differential to D of C on Cn plus 1 plus Bn plus 2. And I would want this map to commute. And well, you see that if you just send Cn to Cn, that's good enough. So on Cn, it's just the identity. How about A? If I have some A here, and I apply the differential, then it's going to land in dA on this side, plus or minus H of G of A on this side. And if I send it here, since I already told you that the Cn component should go by the identity, is going to go to whatever I send this, that I do not know what it is, but in here it's going to land on H of G of A, plus something perhaps. On the other hand, if I map from A to here, and I want to get something non-trivial here, then I'm going to apply F. I'm sorry, it's G. And the differential from here to here is just apply D of that, which is going to recover my D here, plus taking the map from Bn plus 1 to Cn plus 1, which is this H. So now we just checked what is in this map here. It's just the identity here and the map G here. And that's a map of complexes. So we always have a natural map of complexes from this cone to this cone. Okay, so let's go back here. It's longer than what I thought. So this is the cone I started with. This F is a quasi isomorphism, and I have this this triangle. Now I pick this composition and I put it here, and I construct the cone of that composition. But what I just told you, I have a map here to here, from the cone of this composition to the cone of H. But then I also told you that this guy is invertible. The natural map from A shifted by 1 to CH is invertible. So that means that here I have a map. Now I just shift that guy here. Shifted by -1. And this means that here I have a map. Okay, so now I constructed an object and a commutative diagram here. Okay. Okay, so now I have this object and the commutative diagram here. And then this diagram, of course, commutes only up to homotopy because of the construction of this guy that was only constructed up to homotopy. Now I need to check that this is a quasi isomorphism. But that now is trivial because this is quasi isomorphic to 0. Since this F is a quasi isomorphism, this guy is quasi isomorphic to 0. This means that this is quasi-isomorphic to 0. So if I look at this triangle now, and I look at the long exact sequence in homology, what I would find is that the homology of this is isomorphic to the homology of this, because the homology of this is 0. That means that this map here is a quasi-isomorphism. So that's the construction of this little f prime there. Okay? So this D here is constructed as the cone of this composition H with G, which is here. And so G is the given map, and H is the map from B into the cone of F. So that's how we constructed this D there. Okay, so let's see if we remember how to do how that D construction was. And let's try to construct the composition of two morphisms in the derived category, and let's try to fix it. Well, no, by the way, we already fixed this now. Because now we are given this guy here, and this map here, and this was a quasi-isomorphism. Therefore, we know that this D exists with a quasi-isomorphism here, and this makes everything commute. That's it. So now we know that the definition of the space of homomorphisms in the derived category was well defined. So this proves that the equivalence relation was an equivalence relation, and that we have well-defined morphisms in the derived category. So now let's compose them. So composition is something very similar to this. Here I have these three guys were maps between A and B that I identified. So now I have something slightly different. I have one map between A and B. So this is my C, and this is a quasi-isomorphism. And I have another map between A and B. So this is some, let's use some letter different. I have a map from A to B and a map from B to C. And let's suppose that here I have some C prime, and here I have some C second prime. And I want to compose them. So to compose these two, what I need is to get a map from A to C. That is the composition of these two maps. This, by definition, is a map from A to B, and this, by definition, is a map from B to C in the derived category. So what I need is to compose these two, I need a map from A to C. So certainly this is going to be a map like some C3 primes here. And, well, all I need is that this is a quasi-isomorphism. That's what I need. And certainly if I find something that maps to C prime, making this into a quasi-isomorphism and making this diagram commute up to homotopy, then, well, I will call that, this is going to be a quasi-isomorphism by definition. So this is going to be a map from A to C. So I claim that that composition exists and is unique. So claim this C3 prime with this diagram, making this commutative diagram, exists and is unique in the homotopy category, right? Up to homotopy. Okay, so here, that uniqueness is the same uniqueness as this D here that I never proved. But we did prove the uniqueness of this map here, right? Whatever I put there is isomorphic to this I shifted by 1. So let's prove that that this guy exists. Okay, but then I think this should be the same as what we have now. So we have this C prime, we have this diagram here, and I look at this diagram, this little diagram there. I have this C second prime to B, this C prime to B. This is arbitrary, but this is a quasi-isomorphism. So the little lemma says that this guy exists and it's a quasi-isomorphism. The lemma we just proved apply to the case where this is A, this is B, and this is C, says that I have some D mapping to C, which is a quasi-isomorphism, and that this guy is unique. So that gave us this object. This is a quasi-isomorphism, and this diagram commutes up to homotopy. So this gives us a composition. So that's the composition. And now I need to check that composition is well defined. No, sorry. That composition is a composition. I just told you that composition is well defined because that C3 prime is unique. But now I need to check that composition is associative. And this I don't want to do. So we need to check that the identity is an identity for the composition and that the composition is associative. And perhaps let's do one of them. So suppose I have the identity morphism from A to A. It's just this. And I have a morphism from A to B, which is this. And this F here is a quasi isomorphism. Then what you do is just pick C, map into F. This is a quasi isomorphism composed with the identity is a quasi isomorphism, and here's the identity, and clearly this diagram commutes. So this is the composition of the identity morphism of A with this morphism from A to B, and what I've gotten here is F and the same morphism that I had before. So the identity is an identity. Is a left identity. So we need to check that it's a right identity as well. So if I have the identity on B, and I have some map from A to B, so now this is a quasi-isomorphism. Then again, you just pick the same C. Here you have the identity. Here you have this guy G. And now the map from C to A is F. And the map from C to B is G. And that's exactly the same as this diagram that you have there. So the identity is also a right identity. So the larger diagram is equal to this diagram here. Let's check that composition is associative. Okay, so now I have some A, B, and a map from B to C, and a map from C to D. So I can compose the map from A to B with the map from B to C. So I can compose these maps here. I'm not going to even put names to these two things, to the things that go here and there. So the composition of these two maps is something here that makes this diagram commute up to homotopy. And now I have this guy here that I can compose with the map from C to D. So the composition of these two maps, which is this now is a map from C to D, is this guy here with the map here and here. So in red, we should compose the other way around. I can compose these two maps, and composing these two maps is finding something here. Well, it's finding something here with maps like this. So that's the composition of the map from B to C and then the map from C to D. And then the composition of the map from A to B with this map is find something here with maps to A and maps to this. And I want to claim that these two are the same, that these two compositions are the same. That's associativity. Okay? But then associativity means, well, again, it means that this diagram that I have here is the same as this other diagram that I have there. But that commutativity means that there exists something larger that maps to this and maps to this. Because, and here's the game, right? Oh, I guess I should have done this in a different color. So I claim that there exists something larger that maps with these two. Okay, so let's look at what we have. What we have is this node. This guy is a quasi-isomorphism. That was just the composition, the fact that I had compositions. So this is a quasi-isomorphism. I have this node. That's right. I have this node. And this is a quasi-isomorphism because this is just a composition of a bunch of quasi-isomorphisms. And I just constructed, I'm getting lost myself, so I suppose you too. So let's put names and let's do this again slowly. Otherwise, we're all going to get crazy. So the composition, this is my E, F, G. And I'm going to call E the map A to B, F is the map from B to C, and G is the map from C to D. So let's compose E and F first. And I'm going to write it like this. So I think this is the easiest way of thinking of a composition. So that's the object, and these are quasi-isomorphisms. And then now I can compose this with G. So that's one composition. The other composition is doing F and G first. So this is GF. And then doing the composition with E. So this is GF composed with E. So maps here, maps there. Okay. So that's the diagram. So now I claim that the two guys on top are the same. So let's look at those two guys on top. So let's clean up all the clutter, and what we have is G, F, E, mapping to A, mapping to D, and I have some other G, F, E, mapping to A, mapping to D. And my definition that these two guys were the same map meant that they were equivalent modulo that equivalence relation. And that equivalence relation is that there existed something, this deserves a new name, GH, with maps to this, making this diagram commute up to homotopy. That was the definition that these two guys are the same, that these two maps are the same. So what I need is to construct this H. And this H comes from the fact that I have these diagrams commute. So I need to pick a square, and so be smart enough, pick a square and pick it and do it. So let's check. What are the nodes in common that these two maps have? Okay, so I can just look at this E. This is a quasi-isomorphism. I have this map there, and then H lives on top of those. Okay? So my diagram, my theorem produces an H here. Since this is a quasi-isomorphism, this is a quasi-isomorphism, and it comes with maps like this. And everything commutes up to homotopy. So the whole thing commutes up to homotopy. So that means that this H exists, and therefore these two things are equal, and therefore composition is associative. Okay. So now, and we were forced by this. So our construction forced us to have quasi-isomorphisms being isomorphisms. So it forces us to have this structure. So whenever I have any other category with a functor from my category, so if I have any other category D with a functor from my original category of cochain complexes of A to D that sends a complex to the complex, well, it doesn't matter, to F prime of A, then what we have is our A. This is now in the derived category of A. And we choose the functor from here to here to be that f prime. And that's the factoring that was in the original theorem. In other words, the fact that this satisfies the universal property is trivial. It's absolutely trivial. We were forced to have quasi-isomorphisms being isomorphisms, so these morphisms here go to morphisms here by the definition of that this guy satisfies that quasi-isomorphisms are isomorphisms here. Okay, so we have a category with the universal property. Theorem, this category is triangulated. Well, now we have two things. We have, well, theorem, D of A is triangulated. And moreover, after the fact, what we have is this. We have that cochain complexes of A. We have a functor that just takes an object and it gives you the same object, and it takes a morphism and it gives you the homotopy class of that morphism here. And we have a functor that takes an object and it gives you the same object, and it gives you a homotopy class of a morphism, and it gives you the class of that morphism in the derived category. Of course, any morphism from A to B in this category, you can just put the identity from A to B and think it like this. It's a morphism in the derived category. If you pick any representative of the morphism of K of A from A to B, you get a morphism from A to B in the derived category. If you pick another representative of the same homotopy class, they are going to be, they're going to give you the same mapping homology. That means that these two maps are going to be the same in the derived category. So this functor, this diagram commutes. Now, this is triangulated, and this functor is exact. Okay, so let's prove some of the things. First of all, the shift is the shift. So I needed to construct, for this to be triangulated, the shift is the shift in cochain complexes. T of A is just A shifted by 1 in cochain complexes. That's an equivalence of categories. It's clear that shifting a complex is an equivalence of categories because the inverse functor is just shifting the other direction. Okay? So that's a linear equivalence of categories. That was the only condition for the shift. Now I need to tell you what are distinguished triangles. So distinguished triangles in D of A triangle is distinguished in D of A. Distinguished if it's isomorphic to a triangle of the form A to B to the cone of F to A shifted by 1. So anything that is isomorphic to such a thing, we declare it to be a distinguished triangle. And now I need to check that it satisfies all the axioms. Okay, so by definition, TR1 holds. TR1 required that a triangle, that any map can be extended to a distinguished triangle. Well, that's it. The cone exists. The identity needs to be extended by 0, but then any quasi-isomorphism is extended by 0, because we've checked that the cone of a quasi-isomorphism is quasi-isomorphic to 0, therefore it is isomorphic in the derived category to 0. So that means that TR1 holds. Now, if you have a distinguished triangle, I need to check that that a triangle is distinguished if and only if. So let's say this triangle is distinguished if and only if this triangle is distinguished. But that's trivial again, because this triangle is distinguished by definition if and only if it is isomorphic to a triangle of that form. So let's call this guy H, to the cone of H, to be shifted by 1. So I have these isomorphisms. And if I have these isomorphisms, I claim that I get this isomorphism. So this is just the fact that this guy here, I could just, well, yeah. So this gives you a long exact sequence in homology, and that long exact sequence in homology corresponds to just taking, well, it's what we've done already. I think I've written it explicitly. I'm already late, I'm sorry. Let's quickly write this. So what does it say there? It says that, yeah, so I'm going to start with B and C. So I have B, F, C, the cone. Call that H. Yeah, okay. I think I call this H. The cone of H be shifted by 1. And what I want to get is that ABC. So this is isomorphic to BC. BCA shifted by 1. Be shifted by 1. So that's the datum. Okay. Now remember that I had this situation. Actually, the other way around. I call this H. Remember that we had C, and here I could look at the cone of, let's do it here, A, B, C, A shifted by 1. This is what I started with. But I also have A, B. So if I call this F, the cone of F, A shifted by 1. I want to check that these two are isomorphic. But I also had this B to the cone of F, I guess here, B to the cone of F. Let me call this A. That's a bad idea because H I'm using it in a different way. So let's call this K to the cone of K to be shifted by 1. And that this guy was isomorphic to A shifted by 1. Here be shifted by 1. This is that map F shifted by 1. And here I had C of F. This is this map here, delta, delta. And here is this map K. Okay, so now I think this plus this should prove that these two guys are isomorphic. And I'm not going to take more time of yours. So we checked TR1 and TR2. I'll check TR3 the next time. And I'm not going to check TR4, but I want to construct bounded categories and prove a little. I'll start doing computations on this.